Picture this. The universe stretches endlessly, galaxies drift farther apart, stars fade into darkness until one day, nothing remains but a vast, silent emptiness. Or maybe it all collapses back into a single point, only to explode anew in an endless cycle of cosmic rebirth. The fate of our universe isn't just some distant scientific curiosity. It's the ultimate story of everything, and it matters to every single one of us. What happens when the final curtain falls on existence itself? Today, we're diving into 30 mind-bending theories about the universe's ultimate fate, from the chilling stillness of heat death to the fiery drama of the Big Crunch, and even stranger possibilities that sound ripped from science fiction. Each theory challenges how we see reality, time, and our place in the cosmos. Why does this matter? Because whether the universe ends in frozen silence, a violent tear, or something beyond our imagination, the answer reshapes what it means to exist. Stick around. By the end of this journey, you'll see the cosmos in a way you never have before. And who knows, one of these theories might just keep you up tonight, staring at the stars and wondering which fate awaits us all. Now, let's turn our attention to one of the most widely accepted theories about the universe's fate: the Big Freeze, also known as heat death. Imagine a future so distant it's almost incomprehensible, where the universe has expanded to such an extent that everything we know fades into a cold, lifeless void. This isn't science fiction, it's a scientifically grounded possibility based on the laws of thermodynamics and our current understanding of dark energy. Here's how it unfolds. The universe keeps expanding, driven by dark energy, that mysterious force pushing galaxies apart at an accelerating rate. Over trillions of years, stars exhaust their fuel one by one until no new ones are born. Galaxies grow dark, and black holes, the last remnants of cosmic activity, slowly evaporate through Hawking radiation. Eventually, even they vanish, leaving behind only a sparse sea of particles drifting further and further apart, too distant to ever interact again. The temperature of the universe approaches absolute zero, the point where all motion stops and entropy, the measure of disorder in a system, reaches its maximum. Nothing happens ever again. This grim scenario is rooted in the second law of thermodynamics, which states that in an isolated system like our universe, entropy can only increase. Energy disperses, becoming less usable over time until no work can be done. No light, no heat, no life, just an endless, frozen stillness. Observations of dark energy's accelerating effect on cosmic expansion align frighteningly well with this theory, making it one of the leading candidates for how the universe might end. But why does this matter? Because it forces us to confront the impermanence of everything. If the Big Freeze is our fate, then all structure, all complexity, even the memory of existence itself, will one day disappear into the void. It's a humbling thought, yet also a reminder of how extraordinary it is that we're here at all, in this fleeting moment where the universe is alive with stars, galaxies, and the possibility of life. Next, we'll explore a dramatically different vision, one where expansion doesn't win, but gravity fights back in a spectacular finale known as the Big Crunch. Could the universe collapse in on itself, or is the Big Freeze truly inevitable? Stay tuned. Now, let's consider a starkly different fate for our universe, one where gravity doesn't surrender to dark energy, but instead stages a dramatic comeback. Picture this: after eons of expansion, the universe slows, stops, and then begins to collapse under its own weight. This is the Big Crunch, a cosmic finale where everything, galaxies, stars, even atoms, is crushed back into a single point, a singularity. It's the ultimate reversal of the Big Bang, a mirror image of our universe's fiery birth. How could this happen? It all hinges on gravity's strength versus dark energy's push. Right now, dark energy dominates, accelerating expansion. But if its influence weakens over time, or if gravity gains the upper hand, the universe's expansion could decelerate, halt, and reverse. Imagine galaxies drifting closer, collisions sparking new bursts of star formation before everything is pulled inward. Space itself shrinks, temperatures soar, and the cosmos becomes denser and hotter until it's compressed into an unfathomably tiny, infinitely dense point. This idea isn't just poetic symmetry, it's grounded in cyclical universe models like the oscillating theory. Here, the Big Crunch isn't an end but a reset. The singularity might trigger another Big Bang, birthing a new universe in an endless cycle of expansion and contraction. Some quantum gravity theories, like loop quantum cosmology, suggest these cycles could avoid the singularities of classical physics, replacing them with a quantum bounce where space-time rebounds instead of collapsing infinitely. What's the evidence? While observations currently favor eternal expansion, certain models of dark energy like quintessence, a dynamic field that could decay over time, leave the door open for a big crunch. Even string theory hints at possibilities, with higher dimensional brains colliding to restart the universe. It's a tantalizing what-if that challenges our assumptions about time, entropy, and cosmic destiny. The Big Crunch offers a provocative twist. Perhaps the universe isn't fated for cold oblivion but for a fiery rebirth. Whether it's a one-time collapse or part of an eternal cycle, this theory reminds us that the cosmos might have more surprises in store. Next up, we'll examine an even more violent scenario, one where dark energy doesn't just fade but grows unstoppable, tearing reality apart atom by atom. Could the universe end not with a whimper or a crunch but with a rip? While the Big Crunch paints a picture of cosmic reunification, there's a far more brutal fate our universe might face, one where dark energy doesn't just fade but turns into an unstoppable force. Picture this: instead of collapsing back together, every structure in the cosmos is violently ripped apart, piece by piece, until even atoms can't hold themselves together. This is the Big Rip, a nightmare scenario where the fabric of reality itself unravels. Here's how it could happen. Right now, dark energy is causing the universe to expand at an accelerating rate. But what if this acceleration isn't constant? Some theories propose a form of dark energy called phantom energy, which grows stronger over time. Unlike regular dark energy, phantom energy doesn't just push galaxies apart, it amplifies its own effect, making expansion faster and more extreme with every passing moment. First, galaxy clusters would be torn away from each other, disappearing beyond the cosmic horizon. Next, individual galaxies would be shredded as the space between stars stretches too fast for gravity to hold them together. Then, stars themselves would be ripped from their planetary systems. Planets would disintegrate, their atoms torn apart by the relentless expansion of space. Finally, in the last moments, even the fundamental particles holding matter together, protons, neutrons, and electrons, would be torn asunder. The universe would end not with a bang or a crunch, but with a silent, unstoppable disintegration. Recent research adds even more weight to this terrifying idea. Observations of distant supernova and the cosmic microwave background suggest that if phantom energy exists, the Big Rip could happen sooner than we think, possibly within a few tens of billions of years. Some calculations even suggest that if dark energy's equation of state crosses a certain threshold, the universe could reach this catastrophic endpoint. But what would that actually look like? Imagine standing on a planet watching the sky. First, distant galaxies vanish, then the stars blink out one by one. The ground beneath you begins to shake as the very fabric of space stretches beyond its limits. In the final seconds, even your own body would be torn apart at the atomic level. It's a chilling thought, one that makes the Big Freeze sound almost peaceful by comparison. Why does this matter? Because the Big Rip forces us to confront the most extreme possibilities of dark energy's power. While current observations don't yet confirm phantom energy's existence, the fact that it's even a plausible scenario shows how little we truly understand about the forces shaping our universe. Now let's shift to a completely different idea, one that suggests the universe's end might not be an end at all, but a cosmic reset. Could the Big Crunch and the Big Bang be part of an endless cycle? That's the question we'll explore next. But what if the universe has a way to avoid these catastrophic endings altogether? Let's explore a theory that offers a surprising twist, one where the end is just the beginning in an endless cosmic dance. This is the Big Bounce, a cyclical model where the universe doesn't meet a permanent fate, but instead collapses and rebounds in an infinite loop of renewal. Here's how it works. Instead of a one-way trip to oblivion, the Big Bounce suggests that when the universe reaches maximum compression in a big crunch, it doesn't just vanish into a singularity. Instead, quantum forces take over, creating a rebound effect, a new Big Bang. Picture it like a cosmic heartbeat where each contraction leads to another expansion, endlessly repeating across eternity. This idea isn't just speculative. Loop quantum cosmology, a branch of quantum gravity theory, provides a scientific foundation for the Big Bounce. Unlike classical physics, which breaks down at the singularity of a big crunch, loop quantum cosmology suggests that space-time is granular at the smallest scales. These tiny quantum grains resist infinite compression, acting like a cushion that prevents the universe from collapsing into nothingness. Instead, they trigger a bounce, launching a new cycle of expansion. One of the biggest advantages of this theory, it sidesteps the singularity problem. In classical physics, singularities are points where the laws of physics cease to make sense, like at the center of a black hole or the moment of the Big Bang. But in the Big Bounce model, quantum effects smooth out these extremes, meaning the universe never actually reaches an infinite density. It's an elegant solution that keeps physics intact while offering a cosmic reset button. What's even more fascinating is that this cyclical model could explain some of the mysteries of our current universe. For instance, the uniformity we see in the cosmic microwave background. The afterglow of the Big Bang might be the result of conditions set in a previous cycle. Each bounce could reprocess the universe, leaving behind traces of its past while setting the stage for a new beginning. Of course, the Big Bounce isn't without its challenges. Some critics argue that entropy, the tendency toward disorder, would accumulate over multiple cycles, making each successive universe less orderly than the last. But proponents counter that quantum effects might reset entropy during each bounce, preserving the conditions needed for galaxies, stars, and life to form again. Imagine the implications. If the Big Bounce is real, our universe could be just one in an endless series, with each cycle lasting trillions of years. It's a humbling thought, one that transforms the idea of an end into a mere transition. And while we don't yet have definitive proof, the mathematics behind loop quantum cosmology keeps this possibility tantalizingly alive. Now, let's turn to an even more unsettling idea, one where the universe's fate hinges on a single, invisible flaw in the fabric of reality itself. What if everything we know could vanish in an instant, rewritten by a cosmic accident? That's the terrifying premise of our next theory. But before we dive into the unsettling possibilities of vacuum decay, let's take a moment to appreciate just how delicately balanced our universe really is. The laws of physics as we know them, gravity, electromagnetism, the nuclear forces, all depend on something called the Higgs field, an invisible energy field that gives particles their mass. But what if this field isn't as stable as we think? What if it's merely a precarious ledge and one tiny nudge could send everything tumbling into oblivion? That's the nightmare scenario of vacuum decay. Here's how it could happen. Right now, our universe might exist in what physicists call a false vacuum, a state that appears stable but isn't the lowest possible energy level. Think of it like a ball resting on a plateau. It seems steady, but somewhere out there, a deeper valley, exists a true vacuum. If quantum fluctuations or high-energy experiments like those at CERN accidentally knock that ball off the ledge, the results would be catastrophic. A bubble of true vacuum would form, rewriting the very laws of physics as it expands outward at the speed of light. To grasp the scale of this disaster, imagine a cosmic wildfire. Once ignited, this bubble would race through space, leaving nothing recognizable in its wake. Atoms, stars, even space-time itself would unravel. The forces that hold matter together would cease to function as they do now. It wouldn't just be the end of life, it would be the end of physics as we know it. And because it moves at light speed, we'd have no warning. One moment, everything's normal. The next, reality as we understand it is erased. This isn't just science fiction. The math checks out. The Higgs field's potential instability was first highlighted by calculations in the 1970s, and more recent measurements at the Large Hadron Collider suggest we might indeed be in a false vacuum. The good news, the probability of a spontaneous collapse is astronomically low. The bad news, astronomically low, doesn't mean zero. Over infinite time, it could become inevitable. But here's a twist. If vacuum decay happened somewhere in the distant cosmos, we'd never see it coming. The bubble's edge would arrive without any signal, since even light can't outrun it. Some theorists argue this might have already happened elsewhere, that our observable universe is just a pocket of false vacuum waiting its turn. Now let's shift gears to something even more mind-bending. What if our universe isn't alone at all, but just one page in an infinite cosmic library? That's the multiverse theory, and it's next. Now, let's step into a realm where our universe isn't the only one, where it might just be a single thread in an endless cosmic tapestry. This is the multiverse theory, a concept that stretches the imagination but is rooted in serious physics. Imagine an infinite number of universes, each with its own unique laws, constants, and even fates. Some might collapse in a big crunch, others might tear apart in a big rip, and some could be utterly unrecognizable, with physics so alien we couldn't begin to comprehend them. The idea of a multiverse isn't just wild speculation. It emerges naturally from some of our most robust theories, like eternal inflation and string theory. Eternal inflation suggests that the rapid expansion of space during the Big Bang never truly stopped. Instead, it continues in pockets, spawning new universes like bubbles in a boiling pot. Each of these bubble universes could have different physical constants, meaning gravity might be stronger in one, or electromagnetism weaker in another. Then there's string theory, which proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings. To make the math work, string theory requires extra dimensions, up to 10 or 11 in some versions. These hidden dimensions could fold and twist in countless ways, creating a vast landscape of possible universes. In this view, our universe is just one page in an infinite cosmic library, with each shelf holding a reality governed by different rules. What's fascinating is how this theory reshapes the question of the universe's fate. If our universe is one of many, its end might not be the end of everything, just the closing of one chapter in a much larger story. Some universes could die in fire, others in ice, while new ones are born continuously. It's a humbling thought. Our entire cosmos might be a fleeting experiment in a multiverse where beginnings and endings are as common as raindrops in a storm. Of course, the multiverse remains speculative. We have no direct evidence yet, but the sheer possibility is thrilling. It challenges our place in reality and forces us to ask, if there are infinite universes, are there infinite versions of us? And if so, what fates might they face? For now, these questions linger at the edge of science and philosophy, waiting for the next breakthrough to bring them into focus. But speaking of breakthroughs, let's turn to another mind-bending idea, one where the universe itself might be a projection, like a cosmic hologram. That's next. Now, let's shift our perspective to something even more startling, a universe that might not be as three-dimensional as it seems. Picture this: what if everything we see, touch, and experience is actually a projection, like a hologram? with the real information stored on a distant, two-dimensional surface. This is the holographic principle, a theory that turns our understanding of reality inside out. The idea originated from an unexpected place: black holes. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of disorder, which implied they also have temperature. Stephen Hawking later showed that black holes aren't completely black, they emit radiation and slowly evaporate. But here's the puzzle: if a black hole vanishes, what happens to all the information it swallowed? Quantum mechanics says information can't be destroyed, so this became known as the black hole information paradox. Enter Leonard Susskind, who proposed a radical solution. He argued that the information isn't lost, it's encoded on the black hole's event horizon, the point of no return, like a cosmic fingerprint. This led to a broader idea: perhaps the entire universe works the same way. Just as a 3D hologram can be created from a 2D surface, our universe might be a projection from a boundary we can't see, with all the information about particles, forces, and even time stored on that distant edge. If this is true, it changes how we think about the universe's fate. A holographic universe wouldn't end in the traditional sense. Instead, the information that makes up reality could simply stop being projected, like turning off a movie. Or, if the boundary persists, our 3D experience might dissolve back into its 2D blueprint, preserving everything in a frozen, encoded state. Some theories even suggest this could allow for a rebirth, a new projection from the same data, creating a fresh universe with the same underlying rules. The holographic principle also ties into string theory and quantum gravity, offering a way to reconcile the two biggest frameworks in physics. It's unproven, but experiments like the holometer at Fermilab have tried to detect the pixelation of space-time tiny, holographic grains that would hint at this deeper structure. So far, no smoking gun, but the search continues. What's mesmerizing about this theory is its implication. Reality might be far stranger than we ever imagined. If the universe is a hologram, then its ultimate fate isn't about fire or ice, it's about information, preserved or transformed in ways we're only beginning to grasp. And with that, let's dive into another layer of the cosmic puzzle, one where our entire existence might just be lines of code in an unfathomable simulation. But here's a twist that makes the holographic universe seem almost ordinary. What if none of this is real at all? Let's step into the simulation hypothesis, the mind-bending theory that our universe might just be an advanced digital construct, something like a video game run by an unfathomable intelligence. Imagine for a moment that every star, every atom, even your very thoughts, are lines of code in a cosmic supercomputer. It sounds like science fiction, but some serious scientists and philosophers argue it's not just possible, it might even be likely. The idea gained traction with philosopher Nick Bostrom, who laid out a chilling trilemma. Either civilizations like ours almost always go extinct before reaching advanced stages, or they lose interest in creating simulated realities, or here's the kicker, we're almost certainly living in one. His reasoning: if a civilization could create simulations indistinguishable from reality, and they chose to run even a fraction of them, the number of simulated minds would vastly outnumber real ones. Statistically, the odds wouldn't be in our favor. This ties eerily into the Fermi paradox, the puzzling silence of the universe despite its vastness. If intelligent life is common, where is everyone? One answer: they might be outside the simulation watching. Or worse, we could be an abandoned experiment, a forgotten prototype running on autopilot until the programmers pull the plug. The universe's fate in this scenario isn't about cosmic forces but decisions made in whatever reality exists above ours. A glitch, an update, or simply shutting down the server could erase us in an instant, or reset everything with a new set of physical laws. And then there's consciousness. If we're simulations, are our thoughts and feelings just algorithms? Some argue that if the simulation is detailed enough, it doesn't matter, our experiences are real to us. Others, like philosopher David Chalmers, suggest that consciousness itself might be a fundamental feature of reality, whether simulated or not. The debate rages on with no easy answers. Technologically, the simulation hypothesis is hard to disprove. Some researchers, like Seeler's Bean, propose that if our universe is a simulation, it might have a resolution limit, tiny, pixel-like irregularities in high-energy particles. Others look for mathematical oddities in the fabric of reality, like the way the universe seems to run on coded rules rather than infinite precision. So far, no definitive proof, but the search is as thrilling as the theory itself. Whether you find this idea exhilarating or unsettling, it forces us to confront deep questions. If we're in a simulation, does our purpose change? Does morality? And what happens when or if the simulation ends? For now, it remains one of the most provocative lenses through which to ponder the universe's ultimate fate. And with that, let's turn to another radical idea, one where the cosmos isn't just coded, but constantly recycling itself in an endless dance of destruction and rebirth. Now, shifting our gaze from digital realms back to the fabric of reality itself, we arrive at a cosmic danger hiding in plain sight, the false vacuum collapse. Picture the universe as a vast, unstable hillside, where the ground beneath us seems solid but could, at any moment, give way to a far more stable state. This isn't science fiction, it's a genuine possibility rooted in the behavior of the Higgs field, the invisible energy field that gives particles their mass. Here's the unsettling part: our universe might exist in a false vacuum, a temporary state of stability that isn't the lowest possible energy level. If a tiny patch of this false vacuum were to tunnel into a true vacuum, a more stable state with different physical laws, it would unleash a bubble of destruction. This bubble would expand at the speed of light, rewriting reality as it goes. One moment you're sipping coffee, the next the laws of physics themselves change and atoms can no longer hold together. The Higgs field's metastability is key here. Think of it like a marble resting in a shallow bowl. It seems stable, but a nudge could send it rolling into a deeper valley. In 2012, experiments at CERN confirmed the Higgs boson's mass, revealing that our vacuum might indeed be metastable. The math suggests this catastrophic transition is incredibly unlikely in any given year, but given infinite time, it becomes inevitable. How does this stack up against other quantum doomsdays? Unlike the Big Rip or heat death, vacuum decay isn't about cosmic forces wearing down the universe. It's a sudden, unpredictable overhaul. Compare it to a computer crashing mid-sentence versus slowly running out of battery. Other quantum threats, like strange matter conversion, where a single, strangelet particle could transform Earth into exotic matter, are equally abrupt but far less grounded in current evidence. Vacuum decay, by contrast, is woven into the standard model of particle physics. CERN Large Hadron Collider plays a detective role here. By smashing particles at unimaginable speeds, it probes whether the Higgs field's current state is truly stable. So far, no signs of impending doom, but every new experiment sharpens our understanding. Some theorists, like Sean Carroll, argue that even if a collapse happened, we'd never see it coming. The rewrite would be instantaneous with no warning. Others, like Lisa Randall, suggest higher dimensions might stabilize our vacuum, making collapse impossible. What makes this theory uniquely haunting is its stealth. No dying stars, no collapsing galaxies, just silence, then a flash. It forces us to confront how delicate our cosmic order might be. And yet, it's also a reminder. The universe's fragility is what makes its existence, and ours, so astonishing. Now, let's turn to an idea that flips this instability into a cosmic rhythm, the evaporating model, where collisions between dimensions don't destroy the universe but renew it. Now, stepping away from the quiet terror of vacuum decay, let's explore a theory that turns cosmic destruction into a cosmic rebirth, the evaporating model. Imagine our universe not as a one-time explosion, but as part of an endless cycle, like a phoenix rising from its own ashes. This idea challenges the Big Bang itself, proposing that our universe was born not from a singularity, but from the collision of two higher-dimensional objects called brains. Here's how it works. Picture our universe as a three-dimensional brain floating in a higher-dimensional space. Nearby, there's another brain, parallel to ours but invisible. Over eons, these brains drift closer until they collide. That collision isn't a catastrophe. It's the spark that ignites a new universe. Energy from the impact floods our brain, creating matter, light, and the illusion of a Big Bang. But there's no singularity, no point of infinite density, just a cosmic reset button. What makes this model so elegant? It sidesteps the Big Bang's thorniest problems. For example, cosmic inflation, the rapid expansion of the early universe, is neatly explained by the brain's gentle separation after collision, smoothing out wrinkles in space-time naturally. No need for hypothetical inflation fields or fine-tuned physics. Even the universe's startling uniformity makes sense. The brain's flat, parallel surfaces ensure energy spreads evenly, like paint squeezed between two panes of glass. The evaporating model also answers a deeper question. What came before the Big Bang? Instead of a blank void, there's an endless cycle of collisions. Each Big Bang is just a chapter in a much grander story. This cyclical nature echoes ancient philosophies, from Hindu cosmology to Stoic thought, but it's grounded in modern string theory's mathematics. Theorists like Paul Steinhardt and Neil Turok, who pioneered the idea, argue it's more than poetic, it's testable. How? Look for faint imprints in the cosmic microwave background, the afterglow of the universe's birth. A singular Big Bang would leave chaotic swirls of energy, but a brain collision might create subtler, more orderly patterns. Future telescopes could spot these fingerprints. There's even a tantalizing hint. Some anomalies in the cosmic microwave background align eerily with the evaporating model's predictions. Of course, skeptics point out hurdles. String theory, the foundation of the evaporating model, remains unproven, and the idea of hidden dimensions feels like science fiction, until you remember that gravity's weakness suggests it might leak into other dimensions. The beauty of this theory is its audacity. It doesn't just predict the universe's fate, it rewrites its origin. So while the evaporating model may lack the visceral dread of vacuum decay, it offers something profound: hope. If the universe cycles eternally, then even heat death isn't the end. Just wait a trillion years and those silent, distant brains will meet again, lighting up the darkness with a new beginning. Next, we'll dive into a twist on vacuum decay that's even more unsettling: the Big Slurp, where quantum effects could doom us in an instant. Now, shifting our focus to a theory that brings quantum unpredictability into the mix, let's unravel the chilling possibility of the Big Slurp. This scenario takes the eerie concept of vacuum decay and cranks it up to a cosmic scale, blending it with the strange world of quantum tunneling to create a fate that could strike without warning. Picture the universe as a fragile landscape where the very fabric of reality teeters on a knife's edge. Right now, we exist in what physicists call a false vacuum, a seemingly stable but precarious state, like standing on a frozen lake that could crack at any moment. The Big Slurp suggests that somewhere in the cosmos, a tiny bubble of true vacuum could form spontaneously due to quantum fluctuations. Think of it as a cosmic wildfire sparking in the void, except this fire doesn't just burn, it rewrites the rules of physics itself. Once this bubble appears, it expands at the speed of light, consuming everything in its path. Stars, planets, even atoms wouldn't just be destroyed. They'd be transformed into something unrecognizable, their fundamental properties altered forever. The terrifying part: we wouldn't see it coming. By the time the light from the edge of this bubble reached us, it would already be too late. One moment, the universe exists as we know it. The next, everything is erased in a wave of inevitable change. What makes this different from regular vacuum decay It's all about the trigger. While vacuum decay could be set off by high-energy events like particle collisions, the Big Slurp relies on quantum tunneling, a phenomenon where particles bypass barriers they shouldn't be able to cross. It's as if the universe rolls cosmic dice at every moment, and one unlucky roll could doom everything. But here's a twist. Some scientists argue this might have already happened elsewhere. If other regions of space have collapsed into true vacuum, their bubbles could be racing toward us right now. Others counter that the sheer size of the observable universe makes it statistically unlikely for now. Yet, the unsettling truth remains that we can't rule it out entirely. So, while theories like the Big Crunch or heat death give us the comfort of a distant timeline, the Big Slurp serves as a stark reminder that the universe's fate might not be a slow fade but a sudden, irreversible rewrite. Next, we'll explore a theory that flips this existential dread on its head, the Omega Point, where the cosmos doesn't just end but evolves into something transcendent. But now, let's pivot from cosmic doom to a vision of transcendence, the Omega Point, where the universe's finale isn't an end but an extraordinary leap. This theory weaves together science and spirituality, proposing that the cosmos might not just fade away or collapse, but instead evolve into something unimaginably profound. At the heart of this idea is Teilhard de Chardin, a philosopher and paleontologist who dared to merge theology with evolution. He imagined the universe as a living process, steadily growing more complex until it reaches a zenith, the Omega Point, a moment of ultimate unity where consciousness becomes the driving force of reality. Picture humanity and perhaps all intelligent life converging into a single, boundless mind. It's not just poetic speculation. Modern physicists like Frank Tipler have given it a scientific footing. Tipler's Omega Point theory takes de Chardin's vision and grafts it onto cosmology. He argues that as the universe heads toward its final state, whether a big crunch or an infinite expansion, the sheer density of energy and information could allow for a kind of cosmic computation. In simpler terms, the universe might become a superpowered computer, able to simulate or even become an all-encompassing consciousness. Think of it as the universe waking up to itself, with every thought, memory, and experience preserved in a final, radiant moment. But how could this happen? Tipler points to the laws of physics themselves. If the universe collapses, the energy density would skyrocket, creating conditions where infinite computation could occur in finite time. Even in an expanding universe, advanced civilizations might harness dark energy to sustain this process near the end. The kicker: this wouldn't just preserve consciousness, it could resurrect every being that ever lived, simulated down to the last detail. It's immortality written into the fabric of spacetime. Critics, of course, raise eyebrows. Some call it a modern-day scientific theology, blending wishful thinking with equations. Others question whether the universe's computational limits make it impossible. Yet, the Omega Point challenges us to rethink destiny. Could the universe's purpose be not just to exist but to know itself? As we weigh this against the cold void of the Big Freeze or the chaos of the Big Rip, the Omega Point offers something rare, a finale that feels less like an ending and more like a metamorphosis. Up next, we'll confront a paradox that twists the heat-death theory on its head. What if even in total entropy, life finds a way? Now, let's turn the tables on one of the most grim predictions for the universe, the Big Freeze. What if the so-called heat death isn't as final as it seems? This is where the heat-death paradox comes in, flipping the script on entropy with a daring question. Could randomness breathe new life into a cold, lifeless cosmos? At first glance, the Big Freeze feels inevitable. The universe expands forever, stars burn out, and energy spreads so thin that everything grinds to a halt, a frozen, eternal stillness. But here's the twist: even in this seemingly dead void, quantum mechanics might have a trick up its sleeve. Tiny, random fluctuations at the subatomic level could, given enough time, stir the cosmic pot in unexpected ways. Imagine a universe so vast and old that even the tiniest chance events add up. Over trillions upon trillions of years, these fluctuations might spark something new. Enter the bizarre idea of Boltzmann brains. Named after the physicist Ludwig Boltzmann, these are hypothetical self-aware entities that could pop into existence purely by random chance. Picture this: in an endless sea of chaos, atoms could momentarily arrange themselves into a conscious mind, complete with false memories of a past that never was. It's a haunting thought that the next you might not be you at all, but a fleeting accident in an otherwise empty cosmos. Some scientists argue that if the universe lasts long enough, Boltzmann brains become more likely than actual evolved beings. It's a paradox that twists logic. Why do we remember a structured history if randomness should have made us lonely, momentary flickers instead? But let's push further. What if quantum fluctuations don't just create isolated minds, but entire new universes? In an infinitely old cosmos, even the most improbable events become certainties. A random surge of energy could birth a new Big Bang, resetting the clock in a pocket of the void. This isn't just sci-fi, it's a serious consideration in eternal inflation and multiverse theories. The catch for us: it changes nothing. Any rebirth would happen far beyond our time and space, leaving our fate unchanged. Yet, it cracks open a door to hope. Entropy might not be the end, just a pause before another roll of the cosmic dice. Of course, skeptics pounce. The timescales for these events are so ludicrously long that they might as well be never. And Boltzmann brains, they're more a thought experiment than a realistic prediction, highlighting the weirdness of infinity rather than offering a practical escape from heat-death. But that's the point. The heat-death paradox forces us to wrestle with the deepest questions about time, probability, and the nature of existence itself. So, as we stare into the abyss of the Big Freeze, remember, the universe might have a few surprises left. Whether through quantum quirks or phantom minds, the finale could be stranger than we ever imagined. Next up, we'll venture into the far future, where black holes aren't destroyers but the last keepers of light and energy. Now, let's fast forward to a future so distant it's almost unimaginable: the black hole era. Picture a universe where stars have long since burned out, galaxies have drifted apart, and the only remnants of cosmic order are the darkest, most enigmatic objects in existence: black holes. This isn't just science fiction, it's a chillingly plausible chapter in the universe's ultimate story, where these gravitational giants become the last rulers of space and time. For trillions of years, black holes will be the sole survivors in a cold, expanding cosmos. With no new stars forming and existing ones long dead, these cosmic vacuum cleaners will continue their slow dance, devouring any stray particles or radiation that dare to wander too close. But here's the twist: even black holes aren't eternal. Thanks to a groundbreaking idea by Stephen Hawking, we know they gradually lose energy and shrink in a process called Hawking radiation. So how does this work? Imagine the edge of a black hole where gravity is so intense that not even light can escape. According to quantum mechanics, empty space isn't truly empty. It's a seething foam of virtual particles popping in and out of existence. Normally, these particles annihilate each other instantly. But near a black hole's event horizon, something strange happens. One particle might fall in while the other escapes, stealing a tiny bit of the black hole's energy in the process. Over mind-boggling timescales, this slow leak causes the black hole to lose mass, eventually evaporating entirely in a final, faint burst of radiation. What's left after the last black hole vanishes? A universe so sparse it's almost unrecognizable, just a thin soup of photons and leptons, the lightest particles, drifting through an endless, dark expanse. No planets, no stars, no structures of any kind, just silence. It's a stark contrast to the vibrant cosmos we know today, where galaxies blaze with light and energy. But this raises an eerie question: could anything survive this era? Hypothetically, advanced civilizations might find refuge near black holes, harvesting their energy to cling to existence. Some theories even suggest that black holes could become computational havens, using their immense gravity to power thought processes in ways we can't yet fathom. Yet, even these last outposts would face the inevitable as black holes evaporate, leaving no trace behind. The black hole era forces us to confront the sheer scale of cosmic time, a reminder that everything, even the mightiest structures in the universe, is fleeting. But it also hints at something profound. In the face of such vast emptiness, the stories we tell about the cosmos, the questions we ask, and the mysteries we chase become all the more meaningful. Up next, we'll explore how dark energy, the unseen force driving the universe apart, could reshape this distant future in ways we're only beginning to understand. Shifting our gaze from the distant black hole era, let's turn to a force that's shaping the universe's fate right now: dark energy. This mysterious entity makes up about 68% of the cosmos, and it's the reason our universe isn't just expanding, it's accelerating. But what if dark energy isn't as constant as we think? What if it evolves over time, rewriting the destiny of everything? For decades, scientists assumed dark energy was a fixed property of space, described by Einstein's cosmological constant. Yet newer theories like quintessence suggest it might be dynamic, growing stronger or weaker as the universe ages. Imagine dark energy as a dimmer switch rather than an on-off button. In some scenarios, it could fade, allowing gravity to regain control and pull everything back together in a big crunch. In others, it might surge, tearing atoms apart in a big rip long before black holes ever dominate. Quintessence models propose that dark energy could be a field, similar to the Higgs field, but one that changes over cosmic time. Unlike the static cosmological constant, this field could interact with matter or even itself, altering its energy density. Some versions predict a future where dark energy weakens, slowing the universe's acceleration. Others warn of a phantom scenario where it grows infinitely powerful, escalating expansion until space-time itself fractures. The stakes are dizzying. If dark energy weakens, galaxies might one day merge again, reversing the isolation of the black hole era. But if it strengthens, even black holes could be ripped apart before they fully evaporate. The key to predicting this lies in measuring the universe's expansion rate with extreme precision. Missions like the Euclid telescope are doing just that, hunting for tiny fluctuations in dark energy's behavior. What makes this so fascinating is the sheer unpredictability. Dark energy's evolution could render every other theory we've discussed obsolete. It's a reminder that the universe isn't just a clock winding down, it's a story with twists we haven't yet imagined. Up next, we'll confront an even stranger possibility: a cosmos where time itself runs out, leaving reality frozen in an eternal instant. Now picture this: what if the universe's story doesn't end with fire, ice, or even a rip in space-time, but with something far more unsettling: time itself simply stopping? This isn't science fiction, it's a serious possibility in quantum gravity, where the very fabric of reality could one day freeze like a clock with hands stuck in place. The idea of time's end stems from the strange marriage of Einstein's relativity and quantum mechanics. In relativity, time is dynamic, bending around massive objects like black holes. But in the quantum world, time might not be fundamental at all, just an emergent property that vanishes under extreme conditions. Some theories, like loop quantum gravity, suggest that in a universe where entropy maxes out and nothing changes, time loses all meaning. Imagine a film reel where every frame is identical: no motion, no cause and effect, just an infinite snapshot. To grasp this, think of a frozen clock. Normally, its ticking marks the passage of time, but if time itself ends, the clock isn't just stopped, it ceases to have any future or past. There's no before or after, just an eternal now. Philosophers like Julian Barber argue this could be the universe's ultimate fate. a state of perfect stillness where every particle, every force reaches equilibrium. No more stars being born, no black holes evaporating, just a cosmic pause button pressed forever. The implications are mind-bending. Without time, even concepts like the end or eternity collapse. There's no counting trillions of years, no counting down to a final moment, just an instant stretched into infinity. Some physicists tie this to the holographic principle, where time emerges from deeper, timeless laws encoded on the universe's boundary. Others connect it to Boltzmann brains, those random fluctuations that might spawn consciousness in a dead universe. If time ends, could a Boltzmann brain even form, or would it be trapped in that frozen instant? What's chilling is how little we know. Time's end isn't like the Big Crunch or heat death where we can trace cause and effect. It's a total rewrite of reality's rules. Up next, we'll explore a radically different vision, a universe that doesn't just end but awakens as cosmic consciousness takes center stage. Now let's take a step beyond the frozen clock and consider a universe that doesn't just fade into stillness but awakens to something extraordinary, cosmic consciousness. This idea bridges the gap between philosophy and physics, proposing that the universe might not end in silence but in a grand crescendo of awareness. At the heart of this theory is panpsychism, the view that consciousness isn't unique to brains but is a fundamental feature of reality itself, like space, time, or energy. Think of it this way: if the universe is made of particles that combine to form complex structures, could those same particles also carry tiny sparks of experience? Some scientists argue that even electrons or quarks might have a rudimentary form of consciousness, and as the universe evolves, these fragments could coalesce into a unified, self-aware whole. Integrated information theory, or EIT, adds a scientific framework to this idea. Developed by neuroscientist Giulio Tononi, EIT suggests that consciousness arises from the way information is processed and connected within a system. The more integrated and complex the system, the richer its conscious experience. Apply this to the universe and you get a startling possibility. Over incomprehensible timescales, the cosmos itself could become a single vast mind. Picture galaxies acting like neurons, their gravitational and quantum interactions forming a cosmic neural network. But not everyone is convinced. Critics point out that EIT struggles to explain how subjective experience emerges from pure information. Others argue that panpsychism risks being a poetic metaphor rather than testable science. After all, how do you measure the consciousness of a star or a black hole? And if the universe does achieve some form of unified awareness, would it even resemble anything we recognize as thought, or would it be utterly alien? Yet the vision is compelling. Imagine a universe where entropy doesn't lead to silence but to a kind of order so profound that it births consciousness. Instead of fading into darkness, reality becomes a self-reflective entity, contemplating its own existence. Some even tie this to the holographic principle, suggesting that the universe's boundary might encode not just physical laws but the seeds of cosmic mind. So where does this leave us? Whether cosmic consciousness is a scientific inevitability or a philosophical mirage, it forces us to rethink the universe's potential, not as a lifeless machine, but as something that might one day wake up and ask, "What am I?" Next, we'll delve into a darker twist on dark energy, where the universe's expansion doesn't just continue, it accelerates beyond control. Now let's shift from the dream of cosmic awakening to a far more violent possibility, the phantom Big Rip. If you thought dark energy was just a gentle force pushing galaxies apart, brace yourself. This theory takes that idea to a terrifying extreme where the universe doesn't just expand, it shreds itself apart in a cosmic cataclysm. At the heart of the phantom Big Rip is a sinister twist on dark energy. Normally, dark energy is thought to have a constant strength, accelerating the universe's expansion at a steady pace. But phantom energy models suggest something far worse. Dark energy could grow stronger over time, Imagine a car's accelerator pedal being pressed harder and harder with no limit. In this scenario, the repulsive force of dark energy doesn't just keep galaxies drifting apart, it escalates until it overwhelms every binding force in the universe. First, galaxies would be torn from each other. Then, within those galaxies, stars would be ripped from their orbits. As the phantom energy intensifies, even planetary systems wouldn't be safe. Planets would be flung away from their suns. But it doesn't stop there. The horror escalates as atoms themselves are torn apart, nuclei splitting from electrons. Finally, space-time itself would rupture, dissecting reality at the most fundamental level. The universe wouldn't just end, it would be annihilated. The strangest part, this could happen much sooner than you'd expect. Some calculations suggest the phantom Big Rip might occur in as little as 22 billion years, a blink of an eye on cosmic timescales. Compare that to the heat death's trillions of years and the urgency becomes chilling. But here's the catch, observational data doesn't fully support this nightmare scenario. Measurements of distant supernova, which help us track the universe's expansion, show dark energy behaving more like a steady force than an escalating one. So far, there's no evidence that its strength is increasing. That doesn't rule out phantom energy entirely, it just means the universe might be giving us a temporary reprieve. Yet the phantom Big Rip remains a haunting what if. It forces us to confront the fragility of reality and the unpredictable nature of dark energy. After all, if dark energy can defy our expectations once, as it did when its acceleration was first discovered, who's to say it won't surprise us again? So while the data leans toward a tamer fate, the phantom Big Rip lingers as a stark reminder. The universe's expansion might not just be a slow fade to black. It could be a scream in the dark, and with that unsettling thought, let's turn to another shadowy player in cosmic doom, the relentless decay of matter itself. Shifting from the violent chaos of the phantom Big Rip, let's confront a quieter but equally inevitable doom, the slow unraveling of matter itself. Entropic doom isn't just about the universe cooling into darkness. It's about the very building blocks of reality crumbling over unimaginable timelines, leaving behind a ghostly void where even atoms can't survive. To understand this, we need to dive deeper than the heat death's cold, lifeless end. The heat death theory suggests that the universe will eventually reach maximum entropy, where all energy is evenly distributed and no work can be done. But entropic doom takes it a step further. It asks what happens to the matter holding everything together. The answer lies in proton decay, a phenomenon where the protons inside atoms, the foundation of all visible matter, could spontaneously disintegrate. Protons are staggeringly stable. Current experiments suggest their lifespan could exceed 10 to the power of 34 years. That's a 1 followed by 34 zeros. But even that incomprehensible timescale isn't forever. Quantum mechanics allows for the possibility that protons might decay into lighter particles, like positrons and neutral pions, given enough time. If this happens, every atom in the universe would gradually dissolve. Stars, planets, even the dust between galaxies, all of it would eventually evaporate into a sea of subatomic particles and radiation. Here's where the math gets mind-bending. If protons do decay, estimates suggest it would take around 10 to the power of 36 years for all matter in the universe to break down. To put that in perspective, the universe is currently only 13.8 billion years old. That's like comparing a single second to trillions of lifetimes of the cosmos. By the time this decay completes, black holes, the last surviving structures, would have already evaporated via Hawking radiation, leaving behind only a thin haze of particles drifting through an endless, lightless expanse. But there's a twist. Proton decay hasn't been observed yet. Experiments like Super Kamiok and in Japan have searched for signs of it for decades with no definitive proof. Some theories, like those in grand unified models, predict it should happen, while others, like the Standard Model, suggest protons might be truly stable. This leaves scientists divided. Is matter eternal, or is its destruction just a question of time? The eerie beauty of entropic doom is that it forces us to grapple with the limits of our knowledge. Even if protons never decay, other quantum processes like quantum tunneling could still dismantle matter over even longer timescales. Imagine iron atoms in cold, dead stars spontaneously fusing into nickel, then decaying into radiation. Given enough time, even the most stable structures could vanish. So while the heat death paints a picture of a frozen, empty cosmos, entropic doom reveals an even darker fate. A universe where not just light and life fade, but the very fabric of reality itself disintegrates. And with that unsettling thought, let's turn to another twist in the cosmic in Game 1 where randomness might just rewrite the rules entirely. After confronting the bleak possibility of matter itself dissolving into nothingness, let's turn to a theory that offers an astonishing twist, a cosmic second chance. Quantum resurrection flips the script on eternal darkness, suggesting that even in a lifeless void, randomness might spark a new beginning. This idea hinges on a remarkable principle in physics called Poincaré recurrence. In simple terms, it states that given enough time, any system, even the entire universe, will eventually return to a state eerily similar to its starting point. Think of it like shuffling a deck of cards. If you shuffle long enough, the cards will eventually fall back into their original order. Now scale that up to the universe. Over unimaginable timescales, quantum fluctuations could rearrange particles in just the right way to recreate the conditions of the Big Bang, birthing a new cosmos from the ashes of the old. But how long would this take? The numbers are staggering. For a universe in thermal equilibrium, a featureless soup of particles at maximum entropy, the time required for a significant fluctuation could be as long as 10 to the power of 10 to the power of 120 years. That's a number so vast it defies comprehension. Yet, in an infinite timeline, even the most improbable events become inevitable. Given enough time, a random quantum jiggle could concentrate enough energy in one place to trigger a new inflationary epoch, restarting the cosmic cycle. Some physicists argue this isn't just speculative fantasy. The math of quantum field theory allows for it, and in an eternally expanding universe, infinity leaves room for every possibility, no matter how unlikely. The catch: this resurrection wouldn't preserve any memory of the past. Any new universe would be entirely disconnected from ours, with its own laws, constants, and perhaps even dimensions. Critics point out two glaring issues. First, if the universe's expansion accelerates forever due to dark energy, reaching maximum entropy, quantum fluctuations might not have the energy to overcome this dispersal. Second, even if a new universe emerged, it wouldn't be our universe reborn, just a statistical accident echoing its structure. Yet the allure of quantum resurrection lies in its audacity. It challenges the finality of heat death, suggesting that eternity holds more than silence. And with that, we pivot to another radical idea, one where the universe's fate isn't just about physics, but about the very nature of reality itself. Now let's stretch our imaginations even further with a theory that blends the eerie emptiness of heat death with one of physics' most mind-bending ideas: the holographic principle. Picture this: the universe doesn't just fade into cold, dark oblivion. Instead, it transforms into a vast, frozen hologram where all the information that ever existed is preserved, but reality as we know it becomes a flat, two-dimensional shadow of its former self. The holographic principle suggests that our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundary, like a cosmic DVD storing everything that happens inside it. This isn't just science fiction. It emerges from serious work in quantum gravity, particularly the anti-de Sitter/conformal field theory, or AD-S/CFT correspondence. In simple terms, this framework proposes that a higher dimensional space like our universe can be mathematically equivalent to a lower dimensional system at its edge. Think of it like a painting that appears three-dimensional but is actually just ink on a flat canvas. Now apply this to the Big Freeze. As the universe expands endlessly, matter and energy thin out to near nothingness and entropy maxes out. But here's the twist. According to the holographic principle, all the information about every particle, every galaxy, every event in cosmic history could still be preserved, not in our fading three-dimensional world, but on a distant, timeless, two-dimensional boundary. The universe wouldn't die so much as it would freeze into an ultra-compressed archive, a cosmic hard drive where the story of reality is etched permanently, even if no one is left to read it. Recent work on AD/CFT has explored how this might play out in a universe dominated by dark energy. Some models suggest that even as space stretches to infinity, the holographic screen at the boundary remains intact, preserving the universe's information in a state of perfect, unchanging order. It's as if the cosmos becomes a fossil, a static, frozen record of everything that ever was. But hold on, does this mean the universe has a built-in backup? Not exactly. While the information persists, it's inaccessible to anything inside the universe itself. No stars, no life, no observers, just an eternal, silent imprint. Critics argue this is little comfort in the face of heat death, but supporters counter that it at least rescues the universe from total oblivion. After all, in this scenario, reality doesn't truly end. It just changes form, like a book locked in a vault, unread but never forgotten. So what's the takeaway? The holographic Big Freeze offers a haunting yet poetic vision of eternity. Not a blank void, but a cosmic monument to existence itself, frozen in time. And with that, we're ready to dive into an even wilder idea. One where the universe's fate isn't just about physics, but about collisions with other realities entirely. Now, let's venture into a theory that turns the universe's fate into a cosmic game of bumper cars. Picture this: our universe isn't alone. It's just one bubble in a frothing sea of infinite universes, each with its own laws of physics, and some of them might be on a collision course with ours. This is the multiverse collision scenario, where the ultimate end isn't about fading or crunching, but about a head-on smash with another universe. According to eternal inflation theory, the fabric of reality is constantly stretching, with new, bubble universes popping into existence like bubbles in a pot of boiling water. Most of these bubbles drift apart forever, but sometimes they collide. If that happens, the results could be catastrophic. Imagine two soap bubbles merging, but instead of a gentle pop, the collision unleashes enough energy to rewrite the laws of physics in both universes. How would this play out? Some models suggest the collision would leave a scorching imprint on the cosmic microwave background, the afterglow of the Big Bang, like a bruise on the sky. Scientists have scoured the data for these scars, but so far, no conclusive evidence has turned up. That doesn't mean it's impossible. The collision might have happened in a direction we haven't observed yet, or the signature could be too faint to detect with current technology. Here's where it gets even stranger. If another universe bumped into ours, the effects might not be uniform. One side of our cosmos could suddenly heat up while the other freezes, or gravity might start working differently in patches of space. Life, if it still exists, would face a reality where the rules change without warning. Critics argue that without observable proof, multiverse collisions remain speculative. But supporters counter that the math checks out. Eternal inflation naturally predicts such events, even if we can't see them yet. And if we ever do spot that telltale bruise in the cosmic background, it would be the ultimate smoking gun, proving we're not just part of a universe, but a multiverse with a violent dating history. So, while the idea of a universe-ending crash sounds like science fiction, it's grounded in real physics. It's a reminder that our cosmos might not die alone. It could take a neighbor down with it. And with that, we're ready to explore an even more unpredictable twist, a universe where randomness itself spawns new beginnings from the ashes of entropy. But what if the universe doesn't need a dramatic crash or a slow fade to meet its end? What if randomness itself could rewrite the rules? Let's dive into the Boltzmann universe, a theory where chaos becomes the architect of reality. Picture a vast, empty void, a universe that's reached maximum entropy, where every particle is evenly spaced and no energy flows. In this lifeless state, the laws of physics say something extraordinary could still happen, a random fluctuation. Just like shuffling a deck of cards long enough will eventually produce an ordered sequence, quantum randomness could, by sheer chance, twist a patch of this dead void into a brand new universe. This idea comes from Ludwig Boltzmann, a physicist who realized that even in total disorder, tiny pockets of order can spontaneously appear. In the far, far future, when our universe has cooled to near absolute zero and all stars have burned out, a single random quantum event might ripple through the void, concentrating energy in one spot. If that fluctuation is large enough, it could trigger a new Big Bang, a cosmic reset button pressed by luck alone. Critics argue this is like winning the lottery an infinite number of times. The odds of a fluctuation creating an entire universe are astronomically low, but here's the catch. If time is truly infinite, even the most improbable events must happen eventually. Supporters point out that this could mean our own universe isn't special. It might just be one lucky roll of the dice in an endless sea of nothingness. This raises a mind-bending question. Does the Boltzmann universe erase the need for a true beginning or end? If randomness can spawn cosmos after cosmos, then the grand narrative of creation collapses into a series of accidents. There's no first universe, no final collapse, just an endless cycle of chaos briefly arranging itself into order before dissolving again. Yet there's a haunting twist. Some versions of this theory suggest that most Boltzmann universes would be short-lived or bizarre, with physics too unstable for life. A lucky few, like ours, might last long enough for galaxies and thinkers to emerge. That means we could be the exception, not the rule, a fleeting moment of structure in an eternity of noise. The debate isn't just academic. If Boltzmann fluctuations are possible, then heat-death isn't necessarily the end. It might just be the quiet before another improbable rebirth. And with that, we're ready to confront a question that even Einstein wrestled with. What if the universe's fate isn't about physics at all, but about the hidden rules that shape reality itself? Now let's turn our gaze to a theory that challenges the very fabric of cosmic destruction, Roger Penrose's cosmic censorship. Imagine a universe where the most violent events, like black holes colliding, follow strict rules, ensuring chaos never spills out unchecked. Penrose's idea suggests that singularities, those infinitely dense, lawless cores of black holes, are always hidden behind event horizons, never exposed to the wider universe. It's as if nature has a built-in failsafe, a cosmic veil preventing the unpredictable fury of singularities from wreaking havoc beyond their boundaries. Why does this matter for the universe's fate? Because if singularities were naked, their infinite gravity and twisted physics could send shockwaves through space-time, distorting reality in ways we can't predict. But cosmic censorship implies a structured, almost orderly end. When black holes merge, a phenomenon we've now observed through gravitational waves, their singularities stay shrouded, obeying this cosmic rulebook. The data from detectors like LIGO and Virgo support this. Even in collisions releasing energy equivalent to billions of supernovas, the aftermath still hides the singularity behind a new, larger event horizon. Penrose's conjecture isn't just about black holes, it hints at a deeper principle governing the universe's demise. If singularities must always be hidden, then the cosmos might avoid a truly chaotic death. Instead of a free-for-all where physics breaks down everywhere, the universe could collapse or transform in a controlled way, with singularities acting like sealed furnaces, burning away matter and energy behind their impenetrable walls. Critics argue that cosmic censorship is more of a hope than a proven law. In extreme scenarios like ultra-fast spinning black holes or high-energy collisions, some models suggest singularities could peak out. If that's possible, all bets are off. An exposed singularity might rewrite spacetime itself, birthing unpredictable phenomena like closed time-like curves, think time loops, or even new universes. But so far, nature seems to favor Penrose's tidy vision. This ties back to the universe's ultimate fate. If cosmic censorship holds, then even in a big crunch or a black hole-dominated era, the end would be strangely elegant, a universe folding in on itself, its most destructive forces kept politely behind cosmic curtains. It's a reassuring thought that amid the chaos there's still a whisper of order, ensuring the cosmos bows out not with a scream but with a calculated silence. And with that, we confront an even stranger possibility, one where the universe's fate isn't just hidden, but encoded in the very fabric of reality. Now, let's venture into a theory that hinges on a particle so elusive it might as well be a ghost, the action. Picture this: tiny, almost undetectable particles floating through the cosmos, silently shaping the fate of everything. Actions were first dreamed up to solve a puzzle in quantum physics, but they've since become a tantalizing key to unlocking dark energy's secrets. These hypothetical particles could be the missing piece that determines whether the universe keeps expanding, collapses, or does something entirely unexpected. Actions are fascinating because they're incredibly light, billions of times lighter than electrons, and barely interact with ordinary matter. That makes them nearly impossible to spot, but not impossible to hunt. Places like CERN, the colossal particle physics lab, are racing to find them. Why? Because if actions exist, they might not just be passive bystanders in the cosmos. Some theories suggest they could influence dark energy, the mysterious force speeding up the universe's expansion. Imagine a cosmic tug-of-war, dark energy pushing the universe apart while actions pull it back together. Here's where it gets wild. If actions have just the right properties, they could cause dark energy to weaken over time or even reverse. That would mean the universe's expansion slows down, stops, and eventually contracts, a dramatic twist in the cosmic story. It's like a pendulum swinging back after reaching its highest point, but there's a catch: actions are still purely theoretical. No one's seen one yet, but the hunt is on. Experiments like CERN Action Solar Telescope are scanning the sun's rays, hoping to catch a glimpse of these phantom particles. Even the tiniest signal could rewrite our understanding of the universe's fate. Critics argue that pinning so much on an unproven particle is risky. After all, dark energy could behave entirely differently, or actions might not play the role we've imagined. But that's the thrill of cosmology. Sometimes the most far-fetched ideas turn out to be true. If actions are real and they do interact with dark energy, we might be looking at a universe that doesn't just fade into cold emptiness or crunch into a singularity, but one that cycles between expansion and contraction in a grand cosmic dance. So, what's at stake? If actions tip the scales against dark energy, the universe's fate could be far more dynamic than we've dared to dream. It's a reminder that even the smallest particles might hold the keys to the biggest mysteries. And with that, we step into an even more mind-bending idea. One where the universe's ultimate fate isn't written in the stars, but in the fabric of reality itself. But what if the universe's fate isn't just about cosmic forces, but about civilizations clinging to survival in the most extreme corners of existence? Let's shift our gaze from particles to paradoxes specifically. The mind-bending idea that advanced civilizations might outlast the universe itself by taking refuge inside black holes. At first glance, black holes seem like the worst real estate in the cosmos, a place where gravity crushes matter into oblivion. But dig deeper, and you'll find theories suggesting they could be the ultimate lifeboats. Picture this: a society so advanced they've mastered physics to the point where they can harness the energy of a spinning black hole, known as a Kerr black hole. Unlike their static cousins, Care black holes rotate, creating a bizarre region called the ergosphere, where space itself is dragged around like water in a whirlpool. Here, energy could theoretically be extracted, a concept called the Penrose process. Imagine a civilization tapping into this cosmic battery, surviving long after stars have burned out. But it gets stranger. Deep inside a Care black hole, physics twists into loops called closed time-like curves, paths where time bends back on itself. For a civilization inside, time might not flow in a straight line at all. They could experience events in cycles, like a record stuck on repeat. Some physicists, like Nobel laureate Roger Penrose, speculate that these loops might even allow information, or life, to persist indefinitely, evading the heat death of the universe. It's like building a fortress where the usual rules of entropy don't apply. Of course, the hurdles are staggering. The tidal forces near a black hole's core would shred ordinary matter, and the radiation from Hawking evaporation, the slow leak of energy that causes black holes to fade, would make long-term survival a nightmare. But advanced civilizations might not be ordinary. They could engineer structures or even biological forms resistant to these extremes, or upload their consciousness into indestructible quantum networks. Critics dismiss this as science fiction, and they're not entirely wrong. We have zero evidence that black holes harbor life, let alone that closed time-like curves are stable enough to support it. But remember, a century ago, black holes themselves were considered mathematical oddities, not real cosmic objects. The lesson: the universe loves to surprise us. So, while the idea of a black hole civilization stretches our imagination, it also stretches our understanding of survival. If intelligent life can adapt to the harshest environments, perhaps the end of the universe isn't an end at all, just a transition into something we can't yet fathom. And with that, we turn to an even grander question. What if our universe's fate isn't just one outcome, but one of countless possibilities in an infinite multiverse? Now, let's zoom out even further, because what if our universe's fate isn't just a solitary event, but a single note in an endless cosmic symphony? Enter the theory of eternal inflation, a mind-bending idea that reshapes how we think about beginnings, endings, and everything in between. At its core, eternal inflation suggests that the Big Bang wasn't a one-time explosion, but part of an infinite, self-replicating process. Picture a frothing ocean where new bubbles of space-time constantly form, each one a budding universe with its own laws of physics. Our universe, just one bubble among countless others, floating in an ever-expanding cosmic foam. In this scenario, the fate of our particular bubble, whether it freezes, crunches, or rips apart, becomes almost trivial. The larger multiverse keeps inflating indefinitely, spawning new universes long after ours has met its end. This raises a fascinating question: could we ever detect these other universes? The answer, frustratingly, is probably no. Bubble universes are thought to be entirely isolated from one another, separated by stretches of rapidly inflating space-time that no signal could ever cross. It's like being in a sealed room with no windows or doors. You might suspect other rooms exist, but you'll never see or touch them. This isolation is what physicists call the pocket universe concept. Our cosmos is a self-contained pocket, forever cut off from its neighbors. But here's where it gets even stranger. Some versions of eternal inflation suggest that these bubbles aren't just random. They could contain wildly different physics. One might have stronger gravity, another might lack dark energy entirely, and yet another could have 6 dimensions instead of 3. In this view, the multiverse is a vast laboratory where every possible universe gets a trial run. Our existence, with its finely tuned constants allowing for stars, planets, and life, might just be a lucky roll of the dice in an infinite casino. Critics, of course, point out the elephant in the room. If we can't observe these other universes, is eternal inflation even science? It's a fair challenge. Theories that can't be tested risk drifting into philosophy. Yet, proponents argue that certain signatures, like anomalies in the cosmic microwave background, might hint at collisions between bubble universes in the distant past. So far, no smoking gun has been found, but the search continues. What eternal inflation ultimately teaches us is humility. Our universe's fate, dramatic as it may seem, could be a footnote in a much grander story, one where beginnings and endings are happening everywhere all the time. Next, we'll explore an even more radical twist. What if the universe's final act isn't destruction, but a transformation into something beyond our current physics? But before we dive into the next mystery, consider this. What if the universe's ultimate fate isn't destruction, but a cosmic library where nothing is ever truly lost? That's the tantalizing idea behind the information paradox end, a theory that ties everything back to one of Stephen Hawking's most famous discoveries. At the heart of this puzzle is the black hole information paradox. For decades, physicists believed that anything swallowed by a black hole vanished forever, erased from existence. But Hawking turned that notion on its head when he showed that black holes slowly leak energy, a phenomenon now called Hawking radiation. Here's the catch: if black holes eventually evaporate, what happens to all the information? The atoms, stars, even entire civilizations they consumed. Quantum mechanics insists information can't be destroyed, yet general relativity says it's gone for good. That's the paradox. Now, imagine a solution where Hawking radiation isn't just random noise, but a cosmic cipher, a scrambled blueprint of everything the black hole ever consumed. Think of it like burning a book. The pages turn to ash, but if you could somehow analyze every wisp of smoke and fleck of char, you might reconstruct the original text. In this scenario, black holes don't destroy information, they encode it in their final bursts of radiation. This means the universe's fate might not be oblivion, but a transformation into a vast holographic archive. Some theorists take this even further, suggesting that if information is preserved, reality itself could one day be reconstructed. Picture a distant future where advanced civilizations, or even natural quantum processes decode Hawking radiation like cosmic archaeologists, piecing together lost universes from their echoes. It's a far-fetched idea, but it offers a poetic twist. The end of our universe might just be the beginning of its next iteration. Critics, of course, point out the gaps. Decoding Hawking radiation is like trying to read a book shredded into a billion pieces, then mixed with a library's worth of confetti. And even if information survives, does it truly matter if there's no one left to interpret it? Yet, this theory challenges us to rethink what the end really means. Maybe the universe isn't heading toward silence, but a whisper, one that lingers long after the stars have faded. So where does this leave us? If the information paradox holds the key to the universe's fate, we might be part of a story that never truly ends, just changes form. Up next, we'll explore an even more radical idea. What if the fabric of reality itself unravels? Now, let's stretch our imaginations even further. What if the universe's fate isn't just about energy or information, but the very dimensions that hold reality together? This brings us to a mind-bending possibility, the collapse of higher dimensions, a theory that could rewrite existence as we know it. String theory, one of the most ambitious frameworks in physics, suggests our universe might have more than the three spatial dimensions we experience every day. Think of these extra dimensions as tightly coiled, smaller than an atom, hidden from our perception but fundamental to the fabric of reality. They're called compactified dimensions, and their stability is anything but guaranteed. Here's where things get eerie. If these higher dimensions were to unravel, like a tightly wound spring suddenly snapping, our familiar three-dimensional space could collapse into them. Picture a house of cards where removing one card causes the entire structure to fold in on itself. In this scenario, galaxies, planets, even the atoms in your body would lose their scaffolding, vanishing into a lower dimensional void. It's not just an end, it's a rewriting of physics itself. Why would this happen? Some models propose that quantum fluctuations or shifts in dark energy could destabilize these hidden dimensions. Imagine a cosmic earthquake shaking loose the foundations of reality. String theorists debate whether these dimensions are eternally stable or precariously balanced, with some equations hinting at catastrophic phase transitions. Critics argue this remains speculative. We've yet to detect even a whisper of extra dimensions. But if they exist, their collapse would be instantaneous and unstoppable. There'd be no warning, no time to react. One moment the universe thrives, the next it's reduced to a shadow of itself. Yet there's a strange beauty here. If dimensions can collapse, might they also expand? Could a future universe reboot with entirely new physical laws? It's a reminder that reality, as we know it, might be just one fragile layer in a far grander cosmic tapestry. Next, we confront an idea that bridges science and something beyond. A fate where the universe's end isn't dictated by physics alone. Now, let's shift our gaze from the equations of physics to a perspective that has shaped human thought for millennia. The idea that the universe's fate might not lie in cosmic forces alone, but in the hands of something beyond our understanding. This leads us to the final and perhaps most profound theory on our list: divine intervention, where the end of all things is guided by a higher power. Across cultures and religions, the notion of a creator determining the universe's destiny is deeply rooted. From Christianity's Book of Revelation to Hinduism's cyclical ages of creation and destruction, these narratives often depict an intentional, purposeful conclusion. But could there be a meeting point between theology and modern cosmology? Enter the fine-tuning argument. Scientists have long marveled at how precisely the laws of physics seem calibrated for life to exist. Change gravity's strength by a fraction, or tweak the nuclear forces, and stars, planets, even atoms might never form. To some, this precision suggests a designer's hand, though others argue it's simply one outcome in a vast multiverse. Then there's the last moment hypothesis, a thought experiment blending science and metaphysics. Imagine a universe where time itself halts, frozen in a single instant, but conscious observers like us perceive an unending present. Philosophers like Frank Tipler have pondered whether a divine force could engineer this state, preserving existence in an eternal now. It's a paradox. The universe ends, yet never truly concludes. Skeptics dismiss this as untestable, yet it raises haunting questions about perception and reality's scaffolding. What makes divine intervention unique is its defiance of purely material explanations. While theories like the Big Freeze or vacuum decay rely on measurable forces, this one rests on faith or, for some, on the limits of science's reach. It's a reminder that humanity's oldest questions about purpose and endings may never fit neatly into equations, yet the dialogue between these worldviews enriches our search for meaning. Whether through physics or philosophy, we're all grappling with the same awe-inspiring mystery: how the story of everything ultimately closes. And with that, we've journeyed through 30 visions of the cosmos's final chapter, each a testament to human curiosity's boundless reach. As we bring this cosmic journey to a close, let's take a moment to reflect on the extraordinary tapestry of possibilities we've unraveled. From the chilling silence of heat death to the explosive drama of the Big Rip, from the philosophical intrigue of simulation theory to the awe-inspiring notion of divine intervention, each theory offers a unique lens through which to ponder the universe's ultimate fate. What's remarkable isn't just the diversity of these visions, but what they reveal about us. Whether grounded in hard science or soaring into speculation, they all stem from humanity's unshakable drive to make sense of the unknown, to find meaning even in the face of oblivion. Think about it, the same curiosity that led ancient cultures to weave stories of cosmic endings now fuels physicists probing the edges of reality. The questions haven't changed, only the tools we use to answer them. And that's the beauty of this exploration. It bridges epochs and disciplines, reminding us that science, philosophy, and even spirituality are all part of the same timeless quest. So here's the real takeaway. The universe's fate isn't just a distant abstraction, it's a mirror. How we imagine the end speaks volumes about how we see existence itself. Is it a cold, mechanical process, a cycle of renewal, a grand design? Your answer might say as much about you as it does about the cosmos. Now we turn the mic to you. Which of these 30 fates resonates most deeply? Does the thought of a big freeze leave you unsettled, or does the poetry of a cyclical universe spark your imagination? Drop your thoughts in the comments. We're eager to hear which theories ignite your wonder or send a shiver down your spine. And if this journey through the cosmos's ultimate mysteries left you hungry for more, don't forget to hit that subscribe button and ring the notification bell. There's always another mind-bending topic just around the corner, and we'd love for you to join us as we keep unraveling the universe's greatest enigmas, one theory at a time. Until then, keep looking up and keep questioning.